Hello, my name is Nathan Hadaway, and this is my Physics 2211 lab report for Lab 3, Black Hole in Orbits. Now, what is this lab? Well, it's a lab where we had a rocket ship as the system, and its surrounding planet and moon are exerting gravitational forces on this rocket, and we kind of um, realize what the how this rocket behaves with those two forces on it. We set the initial velocity of this rocket to be 22,000 meters per second and 30,000 meters per second for its x and y components, respectively. And again, the moon is orbiting the planet in a relatively circular orbit. Before we did this simulation, though, we did a kind of preliminary simulation with only two objects, with a black hole and a orbiting star. The star had a kind of an elliptical orbit, and we can see with the code that I wrote in the middle bottom of the screen. This is most of the important code. This is how I figured out all the p hat and p parallel. This is how I figured out all the variables that I needed, so that eventually, as you can see at the very bottom, I found the mass of the black hole, which is just the universal gravity physics formula, but solved for one of the masses. If you want to look at the entirety of my script, of my glow scripts code, you can look at the URL in the bottom left-hand side of my screen. Next, what I did is I got to the real simulation, or the more complicated simulation but I started with just a moon and the planet. This was pretty easy. You can see how I calculated the force in the bottom right-hand side code. Also, again, all of my code is in the glow script in the bottom right-hand side, the URL there. Uh, but yeah, so the first thing I calculated was I tried to get a circular orbit of the moon around a planet. Then after that, I added the rocket that is on top of the moon. I found an initial velocity so that it didn't crash into the moon or the planet, and then I calculated all the forces and ran the program. Now, what is this lab trying to prove? Well, it's trying to prove this formula in the first equation that I mentioned before. This is the universal gravity physics equation. Um, and while this lab does also use the position and velocity update formulas. Those were more focused on the last two labs. So if you want to learn more about them, you can look at those labs. This lab doesn't focus as much on them, but more on this universal gravity equation. And we can see that this universal gravity equation is true because at least if you're looking at the green line, which is the path of the star in the first program, and the blue line, which is the path of the moon in the second program, these are circular and elliptical orbits, which is what we see in space and nature. Well, nature's a strange word for it, but I guess it is nature in in the universe around us. That's what I'll call it. And then the pink line is the uh, motion of the ship, the position that the ship was at, which seems kind of random, but we can also still see that it's pretty circular, which shows that this equation seems to be compelling, seems to be true. Um, now here is some more of the data that we collected. As you can see in the top left graph, this is from the first simulation where we tried to find the mass of the black hole. The blue line is the what we calculated as the mass at different points, and the red line is what we took as the average, because obviously the mass wasn't changing with time. That was just due to some errors. Some of those errors being we only calculated the force of the gravitational force in the universe. There are other forces that might have been at play. We also said that the black hole and the planet in the first and second simulations, respectively, are not moving. They're simply exactly stationary in the center, which isn't exactly true, as they would have a little bit of movement from the gravitational force of let's say in the first equation, the gravitational force of the star affecting the black hole. Which is actually really interesting because it means, in our solar system, like the sun is technically moving based off of the gravitational force of the Earth on the sun, but obviously it's not that much because the mass of the Earth is much smaller in comparison to the mass of the sun. Other reasons for error could be human error, and we don't have a infinitely small delta t, meaning that there's always going to be some rounding errors and whatnot in the simulations. Some frequently asked questions are what's the difference between the change in momentum or delta momentum and net force? Well, net force is actually equal to the change in momentum divided by the change in time. This is seen in Newton's second law. And this makes sense because if I tell you, I'm not moving and then suddenly I'm moving with a certain momentum down the street, that doesn't tell you how much force I exerted to get there. I would need to tell you how much time it took me, right? I would need to say, well, I started at rest, but then I started sprinting, so it took a very small amount of time, but a very large force to get to that momentum. However, alternatively, I could have, started walking and then slowly gotten up to a jog, and slowly worked my way up, which would be a very small net force, but still got me to the same momentum, showing the differences in changing momentum and net force. Now, what about a system with a black hole, star, planet, and moon? What we need to know to find their positions and see how they would react with each other. Well, that's what we need is we need the masses of all of these and the relative positions in relation to one another. Most importantly, though, we would need to know the mass of the black hole because a black hole having such a massive mass means that it will have the most dominant force, most likely have the most dominant force on the star, the planet, and the moon, just due to its sheer mass. And I can go back to the equation. You can see that the mass one and mass two, mass of both objects are calculated in the force equation. And due to black holes, just again, massive mass, this would be the most important thing to know to be able to calculate forces and try to predict motions of bodies in the system. Thank you for listening.